Okay, so today this lecture we are going to learn about, start off with our adventures of Green's functions in PDEs as opposed to ODEs. So we are going to apply the methods of Green function to PDEs, and this is going to enable us solve the wave equation, the diffusion equation, and the Laplace equation for unbounded domains. We'll also address the problem of inhomogeneous versions of these equations. Okay, so we'll start off with the heat equation. And okay, so let's start. So the heat equation is very simply d phi del phi del t is equal to some d times del squared phi. So these are the same phi's. Okay, so this will be on some Rn times an interval. So Rn is for the spatial part and the interval is the time direction. So we are going to consider the Cauchy problem for the above, where phi obeys the following relation. So phi at Rn and 0 is going to be given by f of x, and the limit of phi of xt, where mod x goes to infinity. So this will be 0 for all t. So the initial, initial profile is of phi is f of x, and we are saying at infinite distances phi of xt is equal to 0. Okay, so what are we going to do first? So at first we are going to take a Fourier transform with respect to the spatial variable. Okay, so that is going to show Fourier transform with respect to the spatial variable. So this gives us del del t. Now phi tilde, and we have transformed the x into k. We have kept t as it is. Okay, this is minus d, and if you do this, it's going to be mod k squared. Phi tilde of k t, and the initial condition is going to look like phi tilde of k0 is equal to some f tilde of k. This equation has a unique solution, and this is given by phi tilde of kt is f tilde k e to the minus d mod k squared t. And phi xt is going to be the inverse Fourier transform of the product of f tilde with this exponential piece. Okay, very good. So now what you need to remember is that the convolution theorem tells us that this is going to be the convolution of the initial. So okay, let me actually write this down. So phi of xt is inverse Fourier transform of f tilde k with of the product f f tilde k with the exponential. E to the minus d k squared t. Okay, mod k squared. So yeah, let's get rid of the d. Let's move this thing in a bit. And let's make sure we get this right. So now what I'm saying is the convolution theorem says that this is going to be the convolution of the initial data with the initial Fourier transform of the Gaussian, right? So let's do this. So f of x, so f of x is inverse Fourier. I'm going to write this as this weird looking f of f tilde. And there's also the Fourier so the inverse Fourier transform of the Gaussian. So remember that this is going to be a form like this. Okay. So if you treat, so remember that this is this. So if you set a squared, so a squared equal to 1 over 4 dt, and you treat t as a fixed parameter in while doing the Fourier transform, what we are going to find is f inverse of e to the minus dt k squared. This is equal to e to the minus x squared by 4 dt by square root of 4 pi dt. Okay, so this is in 1 dimensions, and what you can do is you can do it in n dimensions now, and in n dimensions this looks like the following. So that gives you 1 over 4 pi dt. Now hold to the n over 2 into exponential of, you need to make this into a mod. So this is minus, not r, mod of x squared by 4 dt. Okay. So we are going to call this Sn. Okay. This is in n dimensions. So if you put things together, Sn is the fundamental solution of the wave equation. So phi of x t is then f star Sn of xt, and this is going to be given by 1 over 4 pi dt whole to the n over 2 integral over Rn fy exponential of minus x minus y squared by 4 dt to dny. Okay, provided f is integrable, then this function always obeys the fact that phi goes to 0 as mod x goes to infinity. Okay. For example, if you have, Gaussian as an initial state. So let's say you have f of x is given by some a over pi n over 2 phi naught e to the power minus a mod x squared. So that's a, Gaussian initial state. So if you do that, then what you are going to get, that phi of x t is phi naught and a over 4 pi squared dt whole to the n over 2 integral over Rn exponential of minus mod a mod y squared minus x minus y squared over 4 dt dny. So what you can do is you can complete squares and you can do this integration, and this is going to turn out to be phi naught a over pi by 1 plus 4a dt. I leave you to do this integration and complete squares and get this answer. So exponential minus a mod x squared Okay, so that is going to be the solution here. Okay, very good. So what is going to happen is that if you have an initial Gaussian, it is going to retain its form, and now the square width is going to spread linearly with time, while the total area stays the same. So the peak at x equal to 0 is then going to also drop as t to the minus half. Okay. Now, if you envision a situation where, in the limiting case, it becomes the Gaussian profile becomes more and more sharply peaked around x equal to 0, while maintaining the same amount of heat phi naught, then what happens is that in the limit, f of x becomes just phi naught into delta n of x. So this is where this becomes very, very sharply peaked. So this just in that case, what happens is phi of xy xt just becomes phi naught by 4 pi dt to the n whole to the n over 2. There is Rn, and now you have a delta function and the y, and an exponential of minus x minus y squared by 4 dt to dny. So this just, this is going to just pick out Sn of xt, and that'll be that. So the fundamental solution is the solution where the initial condition is a delta function. All right. So for all times which is greater than t uh, equal to 0. So for all t greater than 0, the initial delta pulse then spreads. I mean as a Gaussian. So let's point out some very interesting features out here. One of the very striking properties of this particular solution is that when you have mod phi, so you have for any finite time t greater than 0, there is a solution which is mod phi which is greater than 0 everywhere throughout all of space, okay, no matter how small, okay. So I mean, uh, unlike say for example the wave propagation, the disturbances out here are going to propagate arbitrarily rapidly, okay. uh, and the fact is that the presence of a heat spike at the origin at t equal to 0 affects the solution at arbitrary great distances. It may be that the and this is done immediately, right? So even if these terms are exponentially suppressed, there is something that is there throughout all of space, okay. So that's a very striking thing. So the mathematically, this sort of boils down to the fact that the heat equation is parabolic and just has one family of these characteristic curves that we were speaking about earlier. Physically, what happens is this is because this equation is not consistent with the special theory of relativity, as you can see very clearly from the equation, right? So you have a single derivative of time here, you have a double derivative of space here, so clearly space and time are not on the same footing. So you don't really have a speed of light. This is if you wish, a non-relativistic system, and in that case you know that the speed of light and any sort of bounding speed is infinity. So instantaneous propagation is something that you can have, okay. So that was trying to solve the heat equation. Now let's move on to trying to add in a forcing term and see how our Green's functions are going to help us, okay. So that's the next bit. So now you want to understand the forced heat equation, okay. So now we have a forcing term on the left hand side on the right hand side. There's some forcing term here, which is going to be called fx and t. Let's call this equation 1. And again, what we do is we have the same homogeneous boundary condition that we had before. So phi at Rn at the initial instant t equal to 0. This is so let's say that this is 0 actually, and limit of mod x going to infinity, phi is equal to 0 for all t. Okay. So the general case with the inhomogeneous equation with the inhomogeneous boundary condition can also be done as we did previously. So we can write down the solution of the inhomogeneous equation with inhomogeneous boundary condition what we can do is we can write phi as the solution of phi of the homogeneous plus phi of f, where f is the one that obeys. So this is the solution to the, so this one is solution to homogeneous equation with inhomogeneous boundary condition, and this one is something that obeys the first equation. Okay, now in order to solve one, we want to now use a Green's function, and now the Green's function is going to be of something that looks like the following. This is going to be functions of x and t and y and some tau, minus d del squared g, again x and t, y and tau is equal to, so this has to be equal to the delta function, the one that we are going to use has to be a delta function of t minus tau as well as a delta n now of x minus y, where g of x0 y tau is equal to 0 by boundary conditions. Okay, so in this case, the formal solution of phi of xt, which is 0 to infinity and integral over all Rn, g of x t y tau, f of y tau, dny d tau. This is something that solves equation 1, right? Very good. Now, what do we want to do? Now, to construct the Green's function, what you're going to do is we are going to Fourier transform. So let's actually call this equation 2. So we're going to Fourier transform equation 2 with respect to the spatial variables, okay? Fourier transform 2 with respect to spatial variables x, okay? So if you do that, so you have to keep in mind that f of delta n x minus y, this is just a plane wave, right? So this is going to be e to the I minus k dot y. You can multiply. Okay, so now what you do is you let's actually plug this in. So what do you have when you, so you have a ddt, and you're also multiplying it throughout by d k, I mean exponential of d k squared t. So then what you're going to obtain is the following: e to the d mod k squared t g tilde of k t y tau. I think it's important to follow the steps here. So it's I k dot y plus d mod k squared t delta of t minus tau. So if you were to find out what G is G tilde of K T Y and tau. This is equal to e to the minus I K dot Y minus D mod K squared T 0 to T e to the D mod K squared U. We're integrating now, so it's D delta U minus tau du. So this is very simply equal to 0 when t is less than tau, and this is e to the minus I K dot Y minus D of mod K squared T minus tau when t is greater than tau. So yeah, just to clarify, or you can just write this down at one go as well instead of trying to write both of these things. So you can just write G tilde G. You can just Fourier transform this again, and you can find G of X T inverse Fourier transforming this Y tau is equal to theta of T minus tau 2 pi to the n integral over Rn e to the I K dot x minus y e to the minus d mod k squared t minus tau dnk. Exactly the same Fourier transform as what we had encountered before, only the arguments have changed. So actually you can just write this down in terms of t minus tau of Sn now x minus y primed t minus tau, where Sn is the one that you had seen before, right? So it's the same fundamental solution that you had before. So we have got that back. Very good. So the fact that the same solution S of n appears in both the solution to the homogeneous equation with inhomogeneous boundary conditions and the solution to the inhomogeneous equation with the homogeneous boundary conditions is not a coincidence. So let's, in order to try and understand this, what we will do is we will go back to the initial thing that we had written down, and we are going to call this something. Let's call this red equation that we have here. Actually, not the red equation, but the equation here. Let us call this equation 2. Okay, let's call this equation 2. And of course, the heat equation, I mean the equation what we have here, let's call this 1. So in order to understand what is happening, let us return to this. But instead, what we want to impose now is that the boundary conditions that we want to impose are phi at Rn, but in a different time slice t equal to tau, let that be equal to some fx, okay? Rather than at, t equal to 0. So we can simply translate the solution that we had earlier and show that this is actually solved by the following. We can solve this by phi n of xt is equal to integral of Rn f of y is n of x minus y t minus tau dny. Let's call this equation A. The initial data at fx equal to of fx at t equal to tau has been propagated by using the fundamental solution for for a time t minus tau to a time t. Okay, so you have the initial data, you propagate it, and you can then just write it in this way. So using the causality from the step function, on the other hand, the solution to the first problem becomes the following. So this is so let me just make sure that this is the homogeneous, this is H. So the solution to the first problem is the following: SF of xt. So this is equal to 0 to t integral over Rn f of y tau is n of x minus y t minus tau dny, and this is integrated also over d tau. Let's call this B. Suppose that for each fixed time t equal to tau, we view the forcing term f yt as an initial condition that is imposed at t equal to tau. So the integral that is in these curly brackets here expresses the solution phi of f to the forced problem as a superposition of the effects from all conditions at time tau earlier than t, and each of these have been propagated by a time t minus tau up to t. Okay, so this upper limit t arises from the step function, and this expresses causality, and the solution at t depends only on this cumulative effect of this initial condition, which is now being applied to this earlier times tau less than t. And the initial conditions applied at tau, for example, can't influence the past. So it's very clear that what is happening is the fact that the solution Sn appears both in this solution of the homogeneous equation with inhomogeneous boundary condition, and this solution to the inhomogeneous equation with the homogeneous boundary condition. This is not something that we have just got out of the air. This has a very clear way of trying, there's a very clear way of trying to understand it. So yeah, I have not written this part down, but these will be in the notes that I share with you. So hopefully that would make your life a little simpler. Okay. So what I will do now, yeah, so I will stop for the moment, and then we will have another session where we look at the wave equation, and then ultimately the Poinsot equation, and before we move on to finally uh, trying to wrap this up by looking at the Laplace equation and the Poisson equation and so on. Okay, so that's the plan. So yeah, hopefully 2 more lectures, or yeah, I mean 2 more lectures, and I think we should be done. Okay, thank you then, and see you soon again.